Okay, so we can continue with our discussion of limit, of formal limit, and we'll see a few examples of proofs using the epsilon delta approach. And for the sake of completeness, I'll also give you the formal definition of one-sided limits and continuity. So, for example, let's say you worked out that the limit as x goes to 1 of x minus 1 over x minus 1 is equal to 1. Okay, now you have to prove it formally. So you worked it out informally, now you have to give a formal proof. Okay, so what do we need to show? We need to show for every epsilon greater than 0, there exists some delta dependent upon epsilon, such that 0 less than absolute value of x minus 1 less than delta implies that the absolute value of x minus 1 over x minus 1 minus the claimed limit 1 is less than epsilon. Okay, but notice something here. If x is not equal to 1, and here 0 less than absolute x minus 1 is guaranteeing that x is not equal to 1, then this x minus 1 divided by x minus 1 is 1. So you've got 1 minus 1, which is 0, which is less than epsilon. Okay, so that means that it really doesn't matter what the delta is. This is 0 less than absolute x minus 1 is doing all the heavy lifting. That's what's giving us the result. We really don't care what epsilon is. But, I mean, the definition is that you have to give some epsilon. So we're going to just give any old epsilon. Okay. So let's just take epsilon is equal to 3. Okay. So then 0 less than absolute x minus 1 less than delta is equal to 3 implies that absolute x minus 1 divided by x minus 1 minus 1 is equal to absolute 1 minus 1 is equal to 0. And 0 is less than epsilon, which is supposed to be any positive number. Okay. So that one was easy. Okay. Let's take another one. Give a formal epsilon delta proof that the limit as x goes to x naught of x is equal to x naught. Okay. Well, what do we need to show? We need to show that for every epsilon greater than 0, there exists a delta dependent upon epsilon, such that 0 less than x minus x naught less than delta implies that x minus x naught is less than epsilon. Well, if I compare both sides of that on that arrow, I would say that delta should equal epsilon. 0 less than absolute value of x minus x naught less than delta equals epsilon implies that absolute value of x minus x naught is less than epsilon. Absolute x minus x naught less than epsilon implies absolute x minus x naught is less than epsilon. Okay, so that one was easy too. Okay, let's try another one. The limit as x goes to x naught of ax plus b is equal to ax naught plus b. Okay. What do we need to show? Okay, we need to show that for every epsilon greater than 0, there exists some delta dependent upon epsilon, such that 0 less than absolute x minus x naught less than delta implies that f of x, that's ax plus b, minus the claimed limit, ax naught plus b, is less than epsilon. Okay, so let's try working backwards. We have absolute value of x. We want ax plus b minus ax naught plus b to be less than epsilon. Okay, so the b's will cancel, so that means we want ax minus ax naught to be less than epsilon. Let's take out the absolute value of a. That means we want absolute value of x minus x naught to be less than epsilon over the absolute value of a. The rest of that is a mystery. Okay. Well, okay. Now each one of these steps is reversible. I can multiply by a and I can add a b and subtract a b, right? So if I have this absolute value of x minus x naught less than epsilon over absolute value of a, that means that absolute of ax plus b minus ax naught plus b will be less than epsilon. Okay, so let delta equal epsilon over absolute value of a. Then 0 less than absolute value of x minus x naught less than delta equals epsilon over absolute value of a implies that the absolute value of ax plus b minus the claimed limit ax naught plus b, that will be less than epsilon. And we're done. Okay, let's try this one. The limit as x goes to 0 of x sine of x is equal to 0. Okay, what do we need to show? We need to show that for every epsilon greater than 0, there is some delta dependent upon epsilon, such that 0 is less than absolute value of x minus, here x naught is 0, less than delta, implies that absolute value of x sine x, that's the function, minus the claimed limit 0, should be less than epsilon. Okay, so let me drop out the zeros. Simplify that as for every epsilon greater than 0, there should be some delta dependent upon epsilon greater than 0, such that 0 less than absolute of x less than delta implies that absolute value of x sine x should be less than epsilon. Okay, now I know that the absolute value of sine x is less than or equal to 1. So the absolute value of x sine of x is less than or equal to the absolute value of x. So it's harder to work with the absolute value of x sine x, but if I can get that is less than or equal to the value, absolute value of x, and I can get absolute value of x less than epsilon, then I would be done. Okay, so absolute value of x less than epsilon implies that absolute value of sine of x sine of x is less than or equal to the value of absolute value of x, which is less than epsilon. Okay, again, so we'll take delta equal to epsilon. We get that absolute value of x less than delta equals epsilon implies that absolute value of x sine x, which is less than or equal to the absolute value of x, is less than epsilon. Okay, so for completeness, let me give you the formal definition of the right-handed limit also, the left-handed limit, and of continuity. So the right-handed limit as x goes to 0 from the right of f of x equals L means that for every epsilon greater than 0, there exists a delta dependent upon epsilon greater than 0, such that 0 less than x minus x naught less than delta implies that absolute value of f of x minus L is less than epsilon. So basically, we've just dropped the absolute value sign because x is supposed to be bigger than x naught in the right-handed limit. For the left-handed limit, something similar. The limit as x goes to x naught from the left of f of x equals L. If for every epsilon greater than 0, there exists a delta dependent upon epsilon greater than 0, such that 0 less than x naught minus x less than delta implies that absolute value of f of x minus L is less than epsilon. And here we've dropped the absolute value and we've written x naught minus x because x naught is supposed to be bigger than x if x is approaching from the left. And the formal definition of continuity. In continuity, what you want to say is that the limit value is the same as the function value. So L, the limit, should be replaced by f of x naught. So the real valued function f is continuous at a point in its domain x naught if for every epsilon greater than 0, there exists some delta dependent upon epsilon greater than 0, so that 0 less than absolute x minus x naught less than delta implies that absolute value of f of x minus f of x naught is less than epsilon. So once again, the L has been replaced by the function value f of x naught, because the limit value is supposed to be the function value for a continuous function. Okay, so let's try this one. I have f of x is equal to 1 for positive x, and otherwise it's equal to minus 1. Okay, take the limit from the left, and we can work out from, our discussions before about directional limits, that the limit from the left should be equal to minus 1. Okay, and let's prove this. And this is, from the left, it looks like a constant function, so this will look like our result for the constant function. For any epsilon greater than 0, let delta equal 10. Then 0 less than 0 minus x less than delta equals 10 implies that absolute value of f of x minus 1 is equal to, well, if x is negative, then the function value is minus 1. So it's absolute value of minus 1 minus minus 1, which is 0, and that's less than any positive epsilon. So once again, delta doesn't really play a role here. Okay. So now, so the idea of formal limits can help you to prove a few very simple limits. For the more complicated functions, it would be more difficult. The big role of this formal limit business is actually to prove the rules that we've been using for limits, things like the limit of the sum is the sum of the limits, and so on. So we will go on to consider that in the next lecture segment.